Namaskar. The topic which I am going to deliver lecture is on plates and their margins. The entire topic is divided into 6 modules: Introduction, History of Plate Tectonics Theory, Plates, their margins and boundaries, Processes at plate boundaries, Causes of plate movement, and the last module is the conclusions. Plate tectonics is a theory that allows earth scientists to explain many geologic processes, particularly those at or near the earth's surface, that is from 0 to 100 kilometers. It is a unifying concept and throws light on the understanding how geologic processes operate and is also a predictive model. Prior to this, many geologic processes were observed, but their underlying causes were not known. For example, why do mountain belts occur, where and when they do? Present theory gives a consistent picture by tying together many different processes. Scientists were aware that the outlines of some continents fit together like pieces of a jigsaw puzzle. In the year 1865, Antonio Snyder suggested they had actually been together at some previous time. Between 1910 and 1930, Alfred Wegener promoted the idea that the continents had moved or drifted around the surface of the earth. He termed the idea as continental drift. What was his evidence for all this? Number 1. Not only do the shapes of some continents match up, but also their geology. Similar rocks and structures, now separated by oceans, line up when the continents are put back together according to their shape. Number 2. Fossils of the same land animals are found on different continents, now thousands of miles apart. Number 3. Glaciers occurred in areas now near equator. Tropical forests occurred in lands now near the poles. When the continents reassembled, glaciated areas now at poles and tropical forests now near equator. But Wegener continental drift theory could not explain the causative mechanism. From 1940 to 1965, various independent lines of evidence showed that the Earth's outer shell was broken up into plates on which the continents rode, just like conveyor belt. Our knowledge of the deep oceans was practically non-existent prior to the 1940s, changed because of the World War II and our desire to hide submarines. This led to know more about the age, composition, geology, shape, etc. of the world's oceans. This gave surprising results, and they are that number 1, oceans are young. They are less than 200 million years old as compared to the continents. Rocks get older as we move away from mid-oceanic ridges, that is called MOR. These have zero age. Continuous chain of undersea mountains. Ocean floor is 99% basalt, very simple geology. Lab experiments show that this you would get if you melted the underlying mantle. Therefore, this is where the melts that form the oceanic crust are coming from. Number 3, magnetic stripping of sea floor. Iron bearing minerals in rocks become magnetically aligned when temperature falls below Curie point, that is 500 to 800 degrees centigrade depending on the mineral. Magnetic field reverses periodically 1 lakh years, that is 1 million year. Every 1 million year periodic reversals of magnetic field takes place. Normal and reverse stripping is symmetric across mid-oceanic ridges, indicating rocks form at mid-oceanic ridges and then spread outward on either side. Number 4. Apparent polar wander. Paleomagnetism on the continent shows either poles have moved or continents have moved relative to poles. Since not all apparent polar wanders show the same motion, poles are not moving, but continents are. They really should be called continent wander curves. Number 5. Earthquakes and volcanoes. Concentrated in specific zones or belts. These mark the boundaries of the plates where all the relative motion is taking place. Most earthquakes are shallow, that is less than 100 kilometers, as at mid-oceanic ridge. However, there are places where the earthquakes go very deep, that is more than 700 kilometers. Mark inclined planes known as Benioff zones, where the plates are moving back down, subducted into the mantle. All of this evidence leads to the following conclusions, that is, sea floor created at mid-oceanic ridge by melting of the underlying mantle, melting due to depressurization, melting as mantle material rises up beneath mid-oceanic ridge. Oceanic crust moves away from mid-oceanic ridge, becomes magnetized, stripped due to periodic magnetic field reversals as sea floor spreading occurs. Continents move with oceanic crust, not through it. They are passive passengers on a moving conveyor belt, like luggage and the baggage carried. Next is oceanic crust consumed at other locations known as subduction zones, marked by a deep sea trench and a zone of descending earthquakes into the mantle. Then the theory of plate tectonics came into existence, which is the result of the combination of continental drift theory and sea floor spreading theories. Now, it is generally understood that the lithosphere floats on the plastic, more mobile and denser asthenosphere. The lithosphere is made up of a mosaic of plates. The plates are rigid and each moves as single unit. There are 7 major very large plates and a dozen or more small plates. Each plate is over 100 kilometers thick. They include continental plates of about 100 to 150 kilometers thick and oceanic plates of about 50 to 100 kilometers thick. Generally, the plate moves over the asthenosphere at rates between 1 and 10 centimeters per year. However, the rates of interactions of adjacent plates approach 20 centimeters per year. There are 3 types of plate boundaries. Number 1, the axis of the oceanic ridge, where the plates are diverging and new oceanic crust is generated. Number 2, transform faults, where the plates slide past each other. Number 3, subduction zones, where the plates are converging and one descends to asthenosphere. The major plates of the world are the Antarctic plate, Australian Indian plate, Eurasian plate, Pacific plate, North American plate, South American plate and African plate, and others are minor plates. Plates. Simplistically, the earth consists of the plates and the plate boundaries, those zones where the plates contact and interact. Observe that 7 different plates are labeled in the cross section. Plates are combinations of 2 units, continents and ocean basins. A plate may be an ocean basin alone, or a continent alone, or a combination of ocean basin and continent. It is possible a plate could be a continent alone, but for this to occur, all edges of the continents would have to be a plate boundary, very rare, perhaps not practically possible. Note that in the cross section, several different ocean basin continent combinations are present, but that is difficult to get a continent with all plate boundaries. Plate boundaries. There are 3 different types of plate boundaries. They are: number 1, divergent. that is mid-oceanic ridges, spreading centers and continental rifts find earthquakes and basaltic volcanism. Convergent, plates come together. In the convergent type of plate boundaries, there are three types of convergence. Number 1, ocean continent. Oceanic lithosphere subducted beneath continental lithosphere. Many earthquakes and andesitic rhyolitic volcanoes occur here. Example, Andes and Cascades, a very dangerous place. Subducted material heated as it goes down. Eventually, it melts, largely due to the presence of water in subducted lithosphere. High temperatures cause water to be released, lowering the melting temperatures in overlying mantle and causing it to melt. Melts rise towards surface and form a chain of volcanoes, that is island arcs and volcanic chains. Examples include Aleutians, Andes, Japan and Cascades Islands. Subduction zones are also the sites of intense metamorphism. The second type of convergence is ocean-oceanic convergence. Cold, denser oceanic lithosphere subducted beneath younger, hotter and therefore less dense oceanic lithosphere. For example, Marianas Trench. The third type of convergence is the continent-continent convergence. Little or no subduction of low density continental lithosphere takes place, usually just earthquakes. For example, Himalayas. The third type of plate boundary is the transform fault boundaries, where plates slide past each other and lots of earthquakes are concentrated in this zone. Example is San Andreas Fault in United States of America. Divergent plate boundaries are also called as spreading axes. Divergent plate boundaries are zones where the plates split and spread apart. The major geological processes in the divergence plate boundaries are rifting and generation of basaltic volcanism, where new oceanic lithosphere is formed. The space between these diverging plates is filled with molten rocks, that is magma from below. Contact with the seawater cools the magma, which quickly solidifies, forming new oceanic lithosphere. This continuous process, operating over millions of years, builds a chain of submarine volcanoes and rift valleys called a mid-oceanic ridge or an oceanic spreading ridge. The present oceanic ridges actually represent the evolved continental or oceanic plate rifting. The divergent plate boundaries are created with the beginning of the continental rifting. The continental rifting begins when the crust is up-arched and stretched so that block faulting occurs. Continental sediments accumulates in the depressions of the down-faulted blocks and basaltic magma is injected into the rift system. Flood basalts can be extruded over large areas of the rift zone during this phase. As rifting continues, the rift valley is created and widened along the rift zone associated with flood basalts. This zone is further invaded by ocean, giving rise to new ocean floor, and new lithosphere is formed, and the divergent plate boundaries are now found as oceanic ridges. Majority of the present plate boundaries are found submerged beneath the sea. However, some of the rift zones are also found in the continental crust. Example, in Africa and North America. The African Rift Valley is in the initial stage of rifting. The Red Sea represents a more advanced stage of rifting with the generation of new oceanic crust. The Atlantic Ocean basin is in advanced stage of rifting. Next, the processes at convergent plate boundaries. Convergent plate boundaries are zones where plates collide. The important geological processes that take place in this zone include subduction, generation of granitic magma, mountain building and metamorphism. The geological processes at the convergent plate boundaries depend on the type of crust involved in the collision of the convergent plates. There are three types of convergent plate boundaries. Number 1. If both the plates at a convergent boundary contain oceanic crust, the zones of the crust is thrust under the margin of the other, and this process at the convergent plate boundaries is called a subduction. The subducting plate descends into the asthenosphere, where it is heated and ultimately absorbed into the mantle. Example, the Japanese islands represents the convergence of two oceanic plates, and the next example is the Marianas Trench. Second type, of the two plates at convergent plate boundaries, if one is a continental crust and other one is an oceanic crust, the continental crust resists subduction and overrides the oceanic plate, which can be subducted to the mantle. Example, Andes and Cascades. Third one, if both the convergent plates contain continental crust, neither of the plates subside. Instead, one can override for a short distance. Ultimately, they are compressed and fused or welded together into a simple continental block. For example, Himalayas in India. The important geological processes at the convergent plate boundaries include island arcs formation, trench formation, melange formation, deformations, and mountain building activity associated with metamorphism. Island arcs are chains of arc-shaped volcanic ridges formed due to collision of plates of two oceanic crust at the convergent plate boundaries. These island arcs are formed generally at the margins of overriding oceanic crust. The subducting oceanic plate at depth undergoes partial melting and generates magma to form island arcs. Melange are soft sediments of the subducting plate at the convergent boundaries and are highly deformed and mixed with basaltic material. The chaotic mass of mud and basalt is called as melange. Trench is formed at the convergent plate boundary of the continental crust and an oceanic crust, where a narrow deep zone is formed, which is usually piled up with melange. Because of the compressional force at the convergent plate boundaries, mountain building activity takes place at the margins of continental crust or plate, which is always associated with deep-seated magmatic activity. Next, processes at transform fault boundaries. This type of boundary occurs where adjacent plates slide horizontally past each other, neither creating nor destroying of the lithosphere without diverging or converging. These boundaries are a special type of fault called transform fault, which is simply a strike-slip fault. The term transform is used here. The kind of motion of plates is changed or transformed. The major causes for the movement of plates are: number 1, convection current; 2, magma injection; 3 is gravity; and 4th is descending plates. Now, let us discuss one by one. Convection currents. This hypothesis suggests that flow in the mantle is induced by convection currents which drag and move the lithosphere plates move above the asthenosphere. Convection currents rise and spread below divergent plate boundaries and converge and descend along convergent plate boundaries. The sources of heat for the generation of convection currents are cooling of Earth's core, radioactivity within the mantle and crust, and cooling of the mantle. Magma injection. This hypothesis invokes the injection of magma at a spreading center, pushing plates apart and thereby causing plate movement. Gravity. Oceanic lithosphere thickens as it moves away from a spreading center, and a cool configuration which might tend to induce plates to slide under the force of gravity from a divergent margin towards a convergent margin. Next is descending plates. This hypothesis suggests that a cold, dense plate descending into the mantle at a subduction zone may pull the rest of the plate with it and thus cause plate motion. Reconstructing the past history of the Earth through plate tectonics. Earth scientists can reconstruct the past history of Earth's continents. Most researchers think plate tectonics began about 3 billion years ago, based on ancient magmas and minerals preserved in rocks from that period. As the continents jostle around the Earth or move around the Earth, they occasionally come together to form giant supercontinents, a single landmass. One of the earliest big supercontinents, called Rodinia, assembled about 1 billion years ago. Its breakup is linked to a global glaciation called snowball Earth. A more recent supercontinent called Pangaea formed about 300 million years ago. Africa, South America, North America and Europe nestled closely together, leaving a characteristic pattern of fossils and rocks for geologists to decipher once Pangaea broke apart. The puzzle igneous rocks form at mid-oceanic ridges and in the subduction zones. Metamorphism occurs, melting takes place, igneous rocks form the continents, and erosion of continents provides sediment and deposition of the sediments in the ocean, and sedimentary rocks are formed. Then sedimentary rocks are subducted. This cycle repeats over and over, perhaps many times. Over billions of years, the amount of continental crust has increased. Tectonics is a tremendous recycling system. Material is transported from one environment to another over hundreds of millions of years. Plate tectonics processes almost certainly have been operating since the formation of the Earth, that is around 4.6 billion years ago. However, the evidence of such processes very early in Earth's history have been masked or obliterated by younger geologic processes and deposits. Present day continents are much older geologically than the seafloor of present day ocean basins. Earliest recognized and dated continental rock was formed about 4.3 billion years ago. This rock has been dated from the continent of Australia. In contrast, the geologically oldest seafloor formed about 180 million years ago. Why this huge difference in geologic age between continental and oceanic rocks? The answer is the new crust formed along the ocean ridge crust is carried away by plate movement and is ultimately recycled deep into the earth along subduction zones. But because continental crust is thicker and less dense than thinner, younger oceanic crust, most does not sink deep enough to be recycled and remains largely preserved on land. Present day continents are fragments of a supercontinent called Pangaea that broke up about 225 million years ago. There were a number of pre-Pangaea supercontinents. The evidences become more and more obscure the farther back in the geologic time. Pangaea itself was the product of accretion of fragments of pre-Pangaea supercontinent. More than 80% of the world's earthquakes and volcanoes occur along or near boundaries of the tectonic plates. Discovery and mapping of the rugged topography, example huge mountain ranges, deep canyons and the Earth is the only planetary body in our solar system that exhibits plate tectonics in action at present as well as in the geologic past. To date, space-based planetary geological studies have not discovered any evidence of extraterrestrial plate tectonics. Plate tectonics occurs because interior of the earth is still hot. It does not occur on the moon or Mars because they are too small and have already cooled. Volcanism continually replenishes atmosphere. Moon and Mars have none or thin atmospheres because little or no volcanism. One of the repercussions and reverberations of the plate tectonics theory is the search for economically important mineral deposits. Thus, theory of plate tectonics not only helps us to understand the dynamics of the earth, but also in the discovery of many new mineral deposits.